We're going to start this off with finding the divergence and curl of f. As a reminder, divergence of f is our del operator dotted with f, and the curl of f is the cross product of the del operator with f, or nabla. I know Ben is fond of the word nabla, the nabla operator.
I'd say fond is a pretty weak word to describe his enthusiasm towards Nabla.
Right. Well, I didn't want to like blow it out of proportion, but his name descriptions on Discord. I've seen what Nabla supremacy. What else was there? The one, the only Nabla or some shit like that. No, that wasn't it. It was something else.
No, it was the pure Nabla.
The pure no. Okay.
Did you know that Nabla Day was like 2 weeks ago?
No, I didn't know there was a day for it. Is this a day you made up?
Maybe.
So let's do our div f. We've got the nabla vector, ddx, ddy, ddz. And this is really x over the square root of x squared plus y squared, right? Plus z squared. Same thing with y. And then z. Insert smiley face here. Smiley face. I'm conserving space. I don't even need that. I'll just point from the smiley face to that. There we go. You know, there's nothing wrong with coming up with your own variables. So let's go through it. DDX on that bad boy. Well, what do we got? It's what we're doing on the DDX, and it's kind of gonna translate to the rest of them. I have x times x squared plus y squared plus z squared to the -1/2, right? I hate doing quotient rule, so I'm going to do the product rule. So if I do that, I've got the derivative of the first. Well, let me do it the back ass way that you guys like to do it, where you take the derivative of the second one first. So -1/2 x squared plus y squared plus z squared. We lower that, so that's -3/2, and then we take the derivative of the inside, which is in terms of respect to x is 2x. And I still have my x out front. So maybe I should put that with the -1/2 over here. And then I could just take the derivative of the first term, and that just leaves me with the second term. So what do I have? I've got x squared on top, a negative x squared on top. And then I've got x squared plus y squared plus z squared to the -3/2. We'll put this down here as 2 to the 3/2. And then I've got plus 1 over that. If I want to get a common denominator, I need to multiply the top and bottom over here by x squared plus y squared plus z squared. If I do that, I'll get a common denominator. Which is interesting because my x terms go away and I'm just left with the other ones. That's kind of neat. So that's the ddx term. I'm guessing, and I'm doing it because I'm just too fucking lazy to do the work. And I'm basing it on how the functions all look the same. I'm guessing the other ones do the same thing, but whatever variable I started with here doesn't show up on top at the end. So we'll make this variable the frowning face to recommend point to that one. And this will be x squared plus y squared there over frowning face here. Also that one. That's ugly. Did I do something wrong in my DDX? Bring the power down, lower it by a power, so down to -3/2. Put in the bottom is 3/2. Okay, the derivative of the inside's 2x. The 2 and the -1/2 cancel. I'm left with the negative x squared. That's right. This one's just drop the x. I got a common denominator by multiplying this by x squared plus y squared plus z squared. Everything is looking right. It's just an ugly derivative or divergence.
I guess in retrospect, usually you would probably take your 1 over frowny face out anyways. Usually.
Right. Yeah, I could rewrite this as excellent point.
That's supposed to be. Oh, okay, right. Oh, geez. Mr. Jones,
Yeah.
I think you made a boo-boo.
Where?
When you did the dot product, you gave yourself a vector.
You're right. I did. These should all be added together. This is what happens when you do DDX as part of it and not do the whole thing. I done fucked that up. Let's relook at what we got going on here. These are all added together. And so that's kind of interesting. We get, okay, that simplifies things a lot. We actually get 2 times x squared plus y squared plus z squared over x squared plus y squared plus z squared to the 3/2, and that simplifies to 2 over the square root of x squared plus y squared plus z squared. Good catch. All right, let me rewrite that vector here because we got to do the curl of f too. It might be handy to know what all those are, though. Oh, wait, shit changes to the other ones. Okay. This problem became a lot longer than I thought it was going to be.
One heck of a warm-up problem.
Right? It didn't look that hard in the book. Nice little
sure
here, do this. And I'm like,
I'm sure they jumped a few steps.
well, it
That's
was one of
okay.
the early numbers, and I'm under the mistaken assumption that a problem that's early in the homework set is easy.
I feel like that's the wrong impression.
It's very much the wrong impression. Curl of f. All right. So I got my curl of f ready to, I wrote out the matrix while I left that up for you guys. That's a z. Does this get any easier on this problem? DDY, this one only affects the bottom, right? So we're gonna have a, let's just look at doing one of those and maybe the pattern will fall out for the rest. DDY of Z times X squared plus Y squared plus Z squared to the -1/2. So the Z doesn't matter, so we're gonna have Z times the derivative of this, which is -1/2.
Wait, this
X squared
matters.
plus,
There's a, when you find the derivative, you're finding the derivative, so multiplying the derivative, the partial of Z by the Y over the square root of X squared plus Y squared plus Z squared. Where are you getting the idea that the second one will not be a problem?
I didn't dump the Z. The Z's still
Oh.
there. With the derivative with respect to Y though, Z is not a Y. So I don't have a product rule. I just have one step. It's one derivative.
Oh, you're just doing, oh, okay. I thought you omitted one of the part of the component.
I'm
Sorry.
not saying Z is irrelevant. I'm not a Z hater. And then we have 2Y on the inside. So the Z, the twos cancel. I've got -YZ over frowny face,
Let's do.
where frowny face is this. All right, so let's see what happens when we do our I. That should follow a pattern. I've got -YZ over frowny face. And I'm going to subtract dz dy, which should give me a dy. I'm subtracting, and it should give me the same thing, but written as zy over frowny face. That looks like that's going to go to 0. Does the same happen with J? If I do J, I should have -xz over frowny face minus dz dx. I should get a -zx here over frowny face, again a 0. And we do it here. I got x's and y's. Same process. -xy over frowny face minus yx over frowny face. And again, 0. So the curl of f on this is the 0 vector. Which means this is irrotational. And it's also the reason why I chose this is because of this. I knew the curl was going to be 0. And I wanted to segue into the next area in this thing. And it took a really long fucking time to segue. I didn't realize it was a 15-minute problem. When the curl of f equals 0, f is the gradient of some potential function. And we're going to have f is a conservative vector field. If we can write f as a gradient of a function like that, we will have a conservative vector field. So we had f was 1 over square root of x squared plus y squared plus z squared, xyz. Can we find phi? That's our next step, finding phi.
What does phi represent again?
What?
What does phi represent? Is it like the
Phi is
angle?
phi is a potential function. It's
Okay.
not an angle here. It's unfortunately they use phi in the book. Several books use phi for this. It's the and it happens in physics too.
Okay.
They use phi occasionally for this. It's a potential function though. So
Okay.
let's find the potential function. How do we go about doing that? So I've got, we're going to call that smiley face, just to simplify this a little bit. I've got X over smiley face, Y over smiley face, Z over smiley face. And I know that's got to equal the gradient of phi, which should be d phi dx, d phi dy, d phi dz. So d phi dx equals x. I'm going to give myself a little bit of room because I'm going to add some stuff in here. X over the square root of x squared plus y squared plus z squared. Now, if I want to find phi, and I know it's just the derivative with respect to x, I can integrate both sides with respect to x. And on the left side, I just get phi. On the right side, what do I get? Let's do a little u sub here. X squared plus y squared plus z squared. So du is the partial of u with respect to x is 2x dx. Partial of u, I'll say. So we'll put a 1/2 over here. Get rid of the 2. And this becomes the integral. And I'm going to put that I need to go back to x for a second. I'm just going to use u for now. This is 1/2 u to the negative 1/2 du. So if I go up a power, it's to 1/2 divided by the power. The 1/2 out front goes away. I'm just left with u to the 1/2 plus some constant. And that is going to be square root of x squared plus y squared plus z squared. Plus some constant. But since we were doing partial derivatives with respect to z, the constant can be a function. Did I say z with respect to x? The constant can be a function of y and z as well. Because the partial derivative of a function that's only got y's and z's in it will be 0 as well. So this is our constant. With respect to x, this is constant. I want to make sure everyone kind of gets that. So like if g was y squared z squared, and I did d dx on this, I'm going to get dg dx equals 0 because there's no x's there. So with respect to x, that's 0. That's why when we say we got a constant, well, it was constant with respect to x. Maybe I'll write that in right there. That's a better thing to do. Write that in right here. C is constant with respect to x. WRT is my shorthand notation for with respect to. And maybe to help remind us, I will write phi as a function of x, y, z over here like this.
Oh, it's with respect to. He literally just, he defined it himself. It's not a usual acronym you see.
It's worth writing down. Not everybody's goes off of audio well. It's omega and then the radius and time. Yeah, I made that up. All right, so we're not done. So we have other things. I've got d phi dy and d phi dz. If I take the derivative of this with respect to phi or y, if I say d phi dy, what does my phi become? Or this is my phi right here. So this is phi. So this part is going to give me the y over the square root of x squared plus y squared plus z squared. And then I'm going to get plus dg dy. That's just taking the derivative with respect to phi. And if I come back up here, I have what d phi dy is. D phi dy is, from up top, it's y over the square root of x squared plus y squared plus z squared. And if I subtract these from both sides, minus, minus, I get dg dy is 0. So g of yz is not a function of y. So maybe we'll call g of yz just h of z. It still might be a function of z. So I'm going to write what my phi is so far. I've got square root of x squared plus y squared plus z squared. And I've got plus h of z. Let me pause, make sure everyone's caught up, and then I'll move that page forward up top. All right. So this is where we're at. And we also had from up top, we had d phi dz equals Z over smiley face. And that's smiley face. So we can finish this off and figure out what phi, I'm off screen. We can figure out what phi is by working off of this. Let's take the partial derivative with respect to Z of both sides there. And this should equal Z over the square root. Oh, I have an HZ plus HZ in there. Plus H prime of Z. And this is d phi dz, which we already have a value for from what we were given in the beginning. This should equal Z over smiley face, which is that. So if I subtract Z over smiley face from both sides, I get H prime of Z equals 0, which means H, when I integrate this, H is not a function of Z at all. It's just a constant. Which means we wrap it all up. We go back up to our phi. We replace H of Z since we know it's not a function of Z. And we've got phi of X, Y, Z is the square root of X squared plus Y squared plus Z squared plus some constant. And that's actually a constant without respect to any variables. So we had to take the derivative 3 times and integrate 3 times. Isn't physics fun? Conservative vector fields show up throughout physics. You got your gravitational field, your electric field, or electrostatic field, or whatever the hell it's called.
That's why the final's 2 days.
Partially. I want to make sure y'all have enough time. I'll give
Yeah,
half
let's
the
make-
problems on one day and half the rest. The problems in chapter 15 tend to take a little bit longer to solve. So if I don't want to test you on just like 2 problems or 3 problems, because what do we got? 8 sections in chapter 15. If I want to test you on more than 3 problems, I got to give you more time to do it. And if we did it during the final hours, you'd only have 2 hours because I can't occupy the room for beforehand or afterhand. So if I do the finals before finals week, I can split it up into 2 days and do get here at 7 in the morning, both times. So effectively giving you guys 4 or 5 hours for the final, just to give you guys some extra time because I care. It's a fault of mine. All right. So similar. Let's find the gradient of 1 over the norm of R if R is given as such. So what is the norm of R? Remember, you square each term and take the square root. So this is kind of similar to our last problem, but a little bit different. in the fact that we don't have an R in it. So we're doing the gradient of that. So we're doing ddx, ddy, ddz of 1 over that.
Well,
Let's just do one of them and we'll translate it to the rest. So ddx of x squared plus y squared plus z squared to the negative 1/2. We bring down the power. We lower the power by 1. And chain rule says we take the derivative of the inside and we get 2x. So the 2's cancel, right? And I get negative x over x squared plus y squared plus z squared to the 3/2. That's my x component of the gradient. And my y component should be similar. I should have negative y over this. And my z component should also be similar.
So is this gradient dotting or crossing the 1 over the magnitude?
What?
it's a scalar times,
Oh, it's a scalar.
scalar times the.
Yeah, the norm is a scalar.
Oh, okay, fair enough.
Scalar times the vector, so it's still that.
So if I factor out, so right now, this is what we're looking at. We've got the gradient of 1 over the magnitude of r. Looks like if I factor out a negative, I got a negative out front. I've got 1 over, it looks like the norm of r cubed, doesn't it? And then I've got x, y, z. Because I factored out the negative and I factored out the denominator. And this is just that cubed. But this is r. So I've got the gradient of 1 over the magnitude of r time equals negative 1 over the magnitude of r cubed times r. And I'm going to rewrite this another way. I'm going to peel off one of those r's, norms of r's, and put it underneath r. Those of you in physics have seen shit like this before. Does that look familiar? That's your gravitational force.
Physics thing, it's the reference.
Oh, if we change it up, if we put. Let me shift it by a little bit. And if I add, let's go with QQ over 4 pi epsilon naught.
Oh my gosh. Isn't that like 56?
Electrostatic force.
Oh my gosh, that is 56. That's what I saw when I was like randomly going into the physics 56 SI. I'm like, look at that. I think that's Coulomb's law or something. I know
So
that-
these are called inverse square fields.
What?
Inverse square fields. We've got the radius squared on the bottom. This is just the R, the unit vector R. R is a unit vector, right? If I divide R by its magnitude, this is the unit vector of R. Those are equations you guys use in physics, right? It's QQ, or do they put Q1, Q2? They might put Q1, Q2.
Because I think they represent the charges of two separate particles, or
Yeah.
yeah. It's very similar to Coulomb's law that you also learned in chemistry as well. Look, it is actually strange stuff. See? That's great. Can you believe it? Math intertwining with physics?
What?
Never seen-
What?
Never seen before. Hashtag not clickbait.
All right. You guys ready for one last little bit? Yeah, I tied in some physics. How you like them apples? I see Eric still writing, so other people must still be writing. So Eric, it's called the inverse square field because there's a square and it's on the bottom. So when we invert something, we flip it over.
I see.
That's why it's called inverse square.
Very creative. Inverse.
I was very pleased with myself when I saw this. I was looking at these problems and we just did 42 part B. And I saw that, I'm like, I know what that is. That's an inverse square field. This is a perfect problem for class. I was very excited because I knew I would take it a step beyond what the problem does and link it to other physics topics. I was very pleased with myself. You all were pleased too, right? That was kind of cool.
Yes.
You did a great. You did a great job. Now we can clickbait the video.
So we started with F and found phi. We can also verify F or phi is a potential function for F. So how would I go about doing that? If phi is the potential function for F, then I left this pin on the wrong side. Rude.
I was fucking around with that.
Then F equals the gradient of phi. So we can take the gradient of phi. So we're going to do ddx. That looks like crap. ddy ddz of phi. So if I do with respect to x, I get sine z plus y cosine x. And nothing from the third term, so that's it for the x component. Now I want to take the partial derivative of phi with respect to y. The first component yields nothing, there's no y's in it. The second component is going to be sine x. Third component, we got a y in the sine, so that'll go to cosine. So z cosine y. And when we do ddz, the first term's got a z in the sine, so that's going to be x cosine z. The second term doesn't have a z, so it goes away. The third term has a z. This just becomes sine y. I'm going to write it below because I wrote really big in the beginning. And does that equal f? If we match it up term by term, sine z plus y cosine x, that's a match. I've got sine x plus z cosine y, that's a match. And this says sine y plus x cosine z. And if I switch the order, I would have x cosine z plus sine y, so that's a match. So yes, this is f. And that means f phi is the scalar or the potential function for f. Now, if we want to check to see, while I still got a few minutes left, if you want to check if f is conservative, is a conservative vector field. And we'll be doing a lot more stuff with conservative vector fields in 15.3. Like the whole section on 15.3 is on conservative vector fields. So if you have questions about it, wait for it. All we have to do is see if it is a conservative vector field. We know since it's the scalar, we know it's since it's the gradient of a scalar potential function. At this point, all we got to do is check to see if the curl of f equals 0. Because for conservative vector fields, the curl of the gradient of a scalar potential function is 0. That's the test for conservative vector fields. And we've already showed that this part is f. And I don't know, do we have time to do that? Give it a try.
5 minutes.
So I'm going to write start setting up the curl of F on another tab or tab shit. Like this is an internet browser. Fucking fail. I've got sine Z plus cosine Y cosine X.
If you're trying to show something, you're not showing it.
I know I'm writing this. I'm writing the curl of F on this on another paper while people are still writing that. All right, I think I don't have it done yet, but I think that everyone's done writing this. Let's check to see if the curl of F is 0. So this was F. My del, my nabla people. Ben, what is it? What's nabla?
DDX, DDY, DDC.
What would I do without you, Ben?
I don't know.
I don't know either.
Not have
So let's figure out, we got 3 minutes, we can do it. What's the I component? DDY of this is just cosine Y, right? Minus DDZ of this is also just cosine Y. And then we've got minus J hat. J hat is ddx of sine Y plus x cosine Z is cosine Z. And ddz of this derivative of sine Z is cosine Z. It's looking like a conservative field because I got a 0 and a 0 so far. ddx of this is cosine X. And ddy of this just drops the Y. We've got minus cosine X there. We do have 0. The curl of F is the 0 vector here. And F was this gradient of a scalar potential function. So this is indeed a conservative vector field.
There's a lot of people that like to that will try to like look for like empty classrooms to go into, just like have a place to study. And those
And that's it, folks.
it's a wrap.
All right.